Fearless concurrency. Handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, where different parts of a program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in these contexts has been difficult and error-prone. Rust hopes to change that. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. Therefore, rather than making you spend lots of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it, rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Fearless concurrency allows you to write code that is free of subtle bugs and easy to refactor without introducing new bugs. Note: for simplicity's sake, we'll refer to many of the problems as concurrent rather than being more precise by saying concurrent and/or parallel. If this book were about concurrency and/or parallelism, we would be more specific. For this chapter, please mentally substitute concurrent and/or parallel whenever we use concurrent. Many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for message passing concurrency, but has only obscure ways to share state between threads. Supporting only a subset of possible solutions is a reasonable strategy for higher-level languages, because a higher-level language promises benefits from giving up some control to gain abstractions. However, lower-level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your situation and requirements. Here are the topics we'll cover in this chapter: how to create threads to run multiple pieces of code at the same time, message passing concurrency, where channels send messages between threads, shared state concurrency, where multiple threads have access to some piece of data, the sync and send traits, which extend Rust's concurrency guarantees to user-defined types as well as types provided by the standard library. Using threads to run code simultaneously. In most current operating systems, an executed program's code is run in a process, and the operating system manages multiple processes at once. Within your program, you can also have independent parts that run simultaneously. The features that run these independent parts are called threads. Splitting the computation in your program into multiple threads can improve performance because the program does multiple tasks at the same time. But it also adds complexity. Because threads can run simultaneously, there is no inherent guarantee about the order in which parts of your code on different threads will run. This can lead to problems, such as race conditions, where threads are accessing data or resources in an inconsistent order, Deadlocks, where two threads are waiting for each other to finish using a resource the other thread has, preventing both threads from continuing. And bugs that happen only in certain situations and are hard to reproduce and fix reliably. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running in a single thread. Programming languages implement threads in a few different ways. Many operating systems provide an API for creating new threads. This model, where a language calls the operating system APIs to create threads, is sometimes called one-to-one, meaning one operating system thread per one language thread. Many programming languages provide their own special implementation of threads. Programming language provided threads are known as green threads, and languages that use these green threads will execute them in the context of a different number of operating system threads. For this reason, the green-threaded model is called the M-to-N model. There are M green threads per N operating system threads, where M and N are not necessarily the same number. Each model has its own advantages and trade-offs, and the trade-off most important to Rust is runtime support. Runtime is a confusing term, and it can have different meanings in different contexts. In this context, by runtime, we mean code that is included by the language in every binary. This code can be large or small depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially, when people say a language has no runtime, they often mean small runtime. Smaller runtimes have fewer features, but have the advantage of resulting in smaller binaries, which make it easier to combine the language with other languages in more contexts. Although many languages are okay with increasing the runtime size in exchange for more features, Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. The green threading M-to-N model requires a larger language runtime to manage threads. As such, the Rust standard library only provides an implementation of one-to-one threading. Because Rust is such a low-level language, there are crates that implement M-to-N threading if you would rather trade overhead for aspects such as more control over which threads run and lower cost of context switching, for example. Now that we've defined threads in Rust, let's explore how to use the thread-related API provided by the standard library. Creating a new thread with spawn. To create a new thread, we call the thread spawn function and pass it a closure. We talked about closures in Chapter 13, containing the code we want to run in the new thread. The example in listing 16.1 prints some text from a main thread and other text from a new thread. 16.1, creating a new thread to print one thing while the main thread prints something else. Note that with this function, the new thread will be stopped when the main thread ends, whether or not it has finished running. The output from this program might be a little different every time, but it will look similar to the following. High number 1 from the main thread, high number 1 from the spawned thread, high number 2 from the main thread, high number 2, and on. The calls to thread sleep. force a thread to stop its execution for a short duration, allowing a different thread to run. The threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads. In this run, the main thread printed first, even though the print statement from the spawned thread appears first in the code. And even though we told the spawned thread to print until I is 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread or don't see any overlap, try increasing the numbers in the ranges to create more opportunities for the operating system to switch between the threads. Waiting for all threads to finish using join handles. The code in listing 16.1 not only stops the spawned thread prematurely most of the time due to the main thread ending, but also can't guarantee that the spawned thread will get to run at all. The reason is that there is no guarantee on the order in which threads run. We can fix the problem of the spawned thread not getting to run or not getting to run completely by saving the return value of thread spawn in a variable. The return type of thread spawn is join handle. A join handle is an owned value that when we call the join method on it, will wait for its thread to finish. Listing 16.2 shows how to use the join handle of the thread we created in 16.1 and call join to make sure the spawned thread finishes before main exits. Saving a join handle from thread spawn to guarantee the thread is run to completion. Calling join on the handle blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means that the thread is prevented from performing work or exiting. Because we've put the call to join after the main thread's for loop, running listing 16.2 should produce output similar to this. High number 1 from the main thread, high number 2 from the main thread, high number 1 from the spawned thread, high number 3 from the main thread, and so on. The two threads continue alternating, but the main thread waits because of the call to handle.join and does not end until the spawned thread is finished. But let's see what happens when we instead move handle.join before the for loop in main, like this. The main thread will wait for the spawned thread to finish and then runs its for loop, so the output won't be interleaved anymore, as shown here. Small details, such as where join is called, can affect whether or not your threads run at the same time. Using move closures with threads. The move closure is often used alongside thread spawn because it allows you to use data from one thread in another thread. In Chapter 13, we mentioned we can use the move keyword before the parameter list of a closure to force the closure to take ownership of the values it uses in the environment. This technique is especially useful when creating new threads in order to transfer ownership of values from one thread to another. Notice in listing 16.1 that the closure we pass to thread spawn takes no arguments. We're not using any data from the main thread in the spawn thread's code. To use data from the main thread in the spawned thread, the spawned thread's closure must capture the values it needs. Listing 16.3 shows an attempt to create a vector in the main thread and use it in the spawned thread. This won't yet work, as you'll see in a moment. Attempting to use a vector created by the main thread in another thread. The closure uses V, so it will capture V and make it part of the closure's environment. Because thread spawn runs this closure in a new thread, we should be able to access V inside that new thread. But when we compile this example, we get the following error. Closure may outlive the current function, but it borrows V, which is owned by the current function. Help: to force the closure to take ownership of V and any other referenced variables, use the move keyword. Rust infers how to capture V, and because println only needs a reference to V, the closure tries to borrow V. However, there's a problem. Rust can't tell how long the spawned thread will run, so it doesn't know if the reference to V will always be valid. Listing 16.4 provides a scenario that's more likely to have a reference to V that won't be valid. 16.4, a thread with a closure that attempts to capture a reference to V from a main thread that drops V. If we were allowed to run this code, there's a possibility the spawned thread would be immediately put in the background without running at all. The spawned thread has a reference to V inside, but the main thread immediately drops V using the drop function we discussed in chapter 15. Then when the spawned thread starts to execute, V is no longer valid, so a reference to it is also invalid. Oh no! To fix the compiler error in listing 16.3, we can use the error message's advice. By adding the move keyword before the closure, we force the closure to take ownership of the values it's using rather than allowing Rust to infer that it should borrow the values. The modification to listing 16.3 is shown in listing 16.5, and it will compile and run as we intend. Using the move keyword to force a closure to take ownership of the values it uses. What would happen to the code in listing 16.4 where the main thread called drop if we use a move closure? Would move fix that case? Unfortunately, no. We would get a different error because what listing 16.4 is trying to do isn't allowed for a different reason. If we added move to the closure, we would move V into the closure's environment, and we could no longer call drop on it in the main thread. We would get this compiler error instead. Use of moved value V. Note, move occurs because V has type standard vec I32, which does not implement the copy trait. Rust's ownership rules have saved us again We got an error from the code in listing 16.3 because Rust was being conservative and only borrowing v for the thread, which meant the main thread could theoretically invalidate the spawned thread's reference. By telling Rust to move ownership of v to the spawned thread, we are guaranteeing Rust that the main thread won't use v anymore. If we change listing 16.4 in the same way, we are then violating the ownership rules when we try to use v in the main thread. The move keyword overrides Rust's conservative default of borrowing, but it doesn't let us violate the ownership rules. With a basic understanding of threads and the Thread API, let's look at what we can do with threads.